many years, the SR-71 Blackbird held the crown as the fastest jet ever built, reaching speeds of more than 2,200 miles per hour. Nothing else came close. But now, a small American startup is about to smash that record with a hypersonic aircraft designed to fly 5 times the speed of sound, about 3,800 miles per hour. At that speed, the air itself turns into a furnace that can melt metal. When it's airborne, it won't just break a record, it will change aviation forever. But first, this machine has to shatter the laws of physics. The race to build a Mach 5 jet. Imagine finishing breakfast in New York and not long after, walking out of an airport in London while the coffee you bought in New York is still warm. That's the kind of trip a small company in Atlanta is trying to make real. Hermeus, a startup based in Atlanta, was founded in the late 2010s by AJ Piplisa and a group of engineers who had already worked on real high-speed flight projects for the US Air Force and companies like SpaceX and Blue Origin. Their plan is simple to say, but hard to do. Build aircraft that can cruise at about Mach 5, link big cities in a fraction of today's time, and give the United States a huge edge in the sky. To see why this matters, it helps to know what Mach actually means. Mach 1 is the speed of sound in air. Near sea level on a normal day, that is about 760 miles per hour. Most long-haul jets today cruise just under that, around Mach 0.8 to Mach 0.9, which works out to roughly 500 to 600 miles per hour, depending on the model and altitude. At those speeds, a flight from New York to London usually takes around 7 or 8 hours. Engineers use the word hypersonic for anything faster than about Mach 5, which means at least 5 times the speed of sound. At those speeds, you are covering close to a mile every second, or several thousand miles in just a couple of hours. Hermeus has said that if you can hold something like Mach 5 across the Atlantic, you could cut a New York-London trip down to around 90 minutes instead of most of a workday. While airlines slowed down after the Age of Concorde, the world's big powers quietly moved in the opposite direction. Russia began showing off new weapons like the avant-garde hypersonic glide vehicle, which rides the thin air near space at many times the speed of sound and can maneuver on the way to its target. China rolled out the DF-17 system, a missile that carries its own hypersonic glider on top. That glider can skip along the upper atmosphere, change direction, and stay off radar for longer than a normal missile fired on the same path. Older missile shields, like the US Navy's Aegis ships or land-based systems built to knock down classic high-arc missiles, were never designed for fast objects that fly lower and can swerve in the middle of their flight. Studies of these new weapons point out the same problem again and again. They move so fast and can change course so late that defenders have far less warning and far less time to shoot. For years, Russian and Chinese systems were being tested in public, while many US hypersonic tests either slipped behind schedule or failed. In that kind of arms race, it is not enough to have one-off test shots that burn up after a single run. The real prize is something that can take off from a runway, race across continents at extreme speed, collect high-value information, or strike a target, then come back to be used again. If one side can fly such machines and the other side cannot, the side with the fast, reusable aircraft can see more, hit faster, and react to crises long before anyone else. That is the gap Hermeus wants to close for the United States. Flying that fast inside the atmosphere is much worse than simply going fast. When a blunt warhead or a space capsule like Crew Dragon comes back from orbit, it slams into the upper air, glows white hot, and endures brutal heat, but only for a few minutes. The nose is wrapped in thick shielding, and the whole point is to slow down and drop into thicker air as quickly and safely as possible. A hypersonic jet is the opposite. It has to climb into the sky, speed up to several times the speed of sound, and then stay there for hours while still carrying fuel, sensors, and maybe even people. At those speeds, the air does not just slide around the aircraft. It hits the nose and leading edges so hard that it turns into a kind of blowtorch. Engineers who study hypersonics describe a huge spike in heat once you get above about Mach 5. Temperatures on sharp front edges can climb to well over 1,000 degrees Fahrenheit, sometimes closer to what you would see in an industrial furnace. Common aircraft metals do not like that at all. Aluminum, which is used in most airliners, softens and melts. Even standard titanium, which is already considered a hot metal, starts to lose its strength. Seals between panels can burn away, fuel lines can overheat, and many normal electronic parts simply cannot survive. That is why people in this field often say that hypersonic flight is not really a speed problem, it is a heat problem. To hold Mach 5 for any useful length of time, you need shells, joints and engines that can sit in a man-made furnace without falling apart. Humanity has been bumping into that wall for decades. Concorde and the SR-71 Blackbird are two famous examples of how far we got before this wall stopped us. Concorde was the first and only supersonic passenger jet that ever entered regular airline service. It cruised at a bit over twice the speed of sound, around Mach 2, which is roughly over 1,300 miles per hour, and flew at heights near 60,000 feet. A typical New York to London trip dropped from around 7 hours on a normal jet to close to 3 hours and 30 minutes, and on its record run, it even managed the trip in under 3 hours. At those speeds, its thin metal skin warmed up so much that the whole airframe grew several inches in flight. Engineers had to leave gaps in the structure for that expansion, and use special aluminum that could withstand the repeated heating and cooling. Still, Concorde paid a price for every bit of that speed. It burned far more fuel than normal passenger jets, produced an ear-splitting sonic boom that kept it off many routes over land, and could carry only about 100 passengers at a time. Those limits made the economics tough. Fuel costs were huge, noise rules were strict, and after a tragic crash near Paris in the year 2000, airlines struggled even more to keep it profitable. By 2003, Concorde was retired. What Concorde did prove, though, was something important. People were willing to pay for much shorter flights. Civil aviation could operate at around Mach 2. But that was still far from the hypersonic speeds a company like Hermeus is now chasing. The SR-71 Blackbird was a different kind of beast. Built in the 1960s by the secretive Skunk Works team at Lockheed, it was a long black spy plane built mostly from titanium. It flew far above most air traffic and set an official airspeed record for jet aircraft in 1976, averaging more than 2,190 miles per hour over a set course, which is more than 3 times the speed of sound. At those speeds, the skin of the aircraft got so hot that fuel tanks could not be fully sealed on the ground, and the jet would leak fuel until the metal expanded in the air and closed the gaps. It needed its own special fuel blend and a whole support fleet of tankers just to do its job. The Blackbird showed what a focused military program with deep pockets could do when the only goal was to go higher and faster than anything else. But even that legend did not reach Mach 5 in level, sustained flight, and it was expensive to fly and maintain. The last SR-71s left US Air Force service near the end of the 1990s. Concorde and the Blackbird are like 2 tall stairs on the same staircase. One proved that paying customers would ride a fast jet, the other proved that a crewed aircraft could live at extreme speed for a while. Mach 5 in a reusable jet is simply the next step up that staircase, and the step is a lot bigger than it looks. Hermeus is trying to climb that step with a very different style from the old government programs. Instead of the slow, paperwork-heavy pace that often marks big defense projects, Hermeus leans into a build it, fly it, break it, fix it mindset. They design a piece of hardware, test it hard, accept that some things will fail, and then roll what they learn straight into the next version. This approach, helped by modern tools like metal 3-dimensional printing and cheap, powerful computer simulations, lets them move faster than older programs that might spend many years on slides and reports before cutting any metal. The US Air Force has taken this seriously enough to put real money on the table. In 2021, the service and venture investors together awarded around $60 million to Hermeus to fund a series of test aircraft under the name Quarterhorse. These unmanned planes are not meant to carry passengers or bombs. Their main purpose is to prove that the airframe and the new engine concept can handle the climb from takeoff, through the sound barrier, and up into the high Mach zone without coming apart. Inside the Mach 5 engine. The scary part of this story is not the shiny metal outside the jet, it is the engine hidden deep in the middle that has to act like 2 completely different machines in one body. This engine is called Chimera, and it is the reason Quarterhorse is more than just a fast drone with cool wings. A normal jet engine is great at the usual job. Pull air in, squeeze it, mix it with fuel, light it, and push it out the back to make thrust. That setup works well from the runway up through high subsonic and low supersonic speeds. But once the air rushing into the intake becomes extremely fast and extremely hot, the spinning blades inside start to become a problem. They cannot grab the flow cleanly anymore, and the front of the engine starts to act more like a brick in a hurricane than a fan in the sky. On the other end of the scale, a ramjet is almost the opposite. Picture a simple metal tube with no big moving parts. At the front, the tube slows and squeezes the incoming air just by its shape. In the middle, fuel is sprayed in and burned. At the back, the hot gases rush out and push the vehicle forward. It is simple and very powerful at high speed, but it has one huge catch. It does almost nothing when the vehicle is slow. A ramjet needs the aircraft to already be racing through the air before it can really work. Chimera blends these two worlds. Engineers call it a turbine-based combined cycle engine, but the idea is simple. At low speed, Chimera behaves like a regular jet engine, with a turbine core doing the hard work. At very high speed, it changes personality and begins to act like a ramjet, with the flow going around the spinning core into a straight duct where fuel is burned. One machine, two playbooks. The hardest part is the handoff between those two playbooks. At some point, the turbine section has to stop doing the main job, and the ramjet duct has to take over, all while the aircraft is already moving faster than a rifle bullet. If the turbine is shut down too early, thrust drops, and the vehicle can slow down or even lose control. If the ramjet is lit too late, the same thing happens. The team at Hermeus calls this narrow window the Valley of Death for the engine, because if you get it wrong, the airplane can fall out of the sky instead of climbing into the history books. To prove they could walk through that valley safely, Hermeus took Chimera to the University of Notre Dame's Turbo Machinery Laboratory. There, engineers built a special test stand that could blast the engine with air that felt, from the engine's point of view, like flight at up to about Mach 4. That meant extremely hot, high-speed air rushing straight into the intake, while the engine stayed bolted to the floor. Over about 5 months of late-night runs in 2022, the joint Hermeus and Notre Dame team pushed Chimera through much of its planned speed range, and finally showed that it could switch from turbine mode to ramjet mode without choking the flow or stalling the engine, from the time they first went to the lab with the plan to the moment they had a working mode switch. The program took roughly under 2 years and a budget of tens of millions of dollars. For a brand new high-speed engine concept, that budget is actually small by defense standards, and the fact that they reached that stage showed this was more than just a promise on a slide deck. The first version of Chimera used a compact General Electric J85 jet core. That little engine has spent decades flying trainers and light fighters, and has a reputation for being tough and predictable, which made it a good starting point for early experiments. But Hermeus always knew they would need a much stronger heart for the aircraft that would actually chase Mach 5 class speeds. For that, they turned to the Pratt & Whitney F100, the same family of engines that has pushed F-15 Eagles and F-16 Fighting Falcons through the sky for roughly 50 years. In its modern versions, this engine can deliver around 29,000 pounds of thrust in afterburner and has built up well over 28 million flight hours in service around the world. Putting a core like that inside Chimera 2 gives Hermeus far more power to work with as the aircraft climbs toward very high speed. At those speeds, the air slamming into the intake is not just fast, it is scorching. Before any compression or burning happens, the air temperature at the front of the engine can climb to several hundred degrees Fahrenheit, hot enough to soften metal parts that are meant to stay rigid. If that hot air is pushed straight into the compressor, the blades and vanes deep inside can overheat, twist, or crack. The solution is something called a pre-cooler. Think of it like a super powerful radiator sitting right behind the engine's air intake. As the air rushes in, it passes through thousands of tiny channels that quickly pull the heat out of it. Because those channels are so small and packed tightly together, the system can remove a huge amount of heat almost instantly without taking up much space. Hermeus plans to build this part using strong nickel-based metals and modern 3D manufacturing methods, so it can handle extreme temperatures while still staying light and durable. When that pre-cooler is paired with the F100, something important happens. The cooler air lets the turbine core run harder and at higher speeds than it was originally designed for, extending how fast the aircraft can go while still using the jet side of the engine. That in turn makes the handoff to the ramjet smoother, because the engine can climb up closer to the sweet spot where a ramjet really shines. Hermeus has already begun running this combined setup, testing its pre-cooler technology directly on an F-100 in dedicated campaigns. Of course, you cannot drag a full jet engine into a normal lab and blow hypersonic air at it every day. So Hermeus is building and now using its own high-energy test site in Jacksonville, Florida, at Cecil Airport. The facility is called HEAT, short for High Enthalpy Air Breathing Test, but all that really means is that it can feed engines with very hot, fast air that mimics the conditions they will see high in the sky at extreme speed. The heat site uses old Navy test cells and a hush house from the 1950s and 1980s that have been upgraded with modern hardware. Inside those thick concrete walls, Hermeus can run the F-100 and later versions of Chimera at high power without shaking nearby neighbourhoods. By owning the facility instead of renting time in a government lab, the company can run test campaigns when it wants, change hardware quickly, and treat engine work more like a fast software project than a slow, one-shot experiment. While the engine work has been racing ahead, the team also had to prove that the strange, compact airframe around it can actually fly. That is where the series of test aircraft called Quarterhorse comes in, starting with something that never left the ground. The very first version, Mach 0, was a dynamic iron bird built to shake out the guts of the airplane. Hydraulics, fuel lines, wiring, landing gear, and the remote control system Hermeus calls the flight deck. Engineers ran it through taxi-like motions, cycled systems, and checked how everything behaved under load until they were confident it was safe to move on. Once Mach 0 had done its job, attention shifted to Quarterhorse Mach 1, the first real flyer. Mach 1 is a high-speed shaped drone powered by a General Electric J-85 engine, the same kind used in older trainer and light fighter jets. It was built with a short, stubby wing that is great for high-speed work, but makes takeoff and landing much more challenging. Hermeus and the United States Air Force took Mach 1 to Edwards Air Force Base in California, where nearly every major American record aircraft has been tested. Ground tests at Edwards focused on high-speed taxi runs, steering, braking, and how the aircraft behaved when it was just barely lifting off the runway. Those trials confirmed that the flight control system could handle things like low-speed lift, heavy wing loading, and the low thrust-to-weight ratio that comes with a small engine in a slippery high-speed shape. Then came the real milestone. In late May of 2025, Mach 1 made its first full flight at Edwards. Remote pilots sitting in a ground station brought the aircraft up to speed, lifted off, flew a planned pattern to check stability and control, and then brought it back for a clean landing. Hermeus says that flight, plus the follow-on sorties, validated its computer models for things like aerodynamics, stability, control laws, fuel systems, and telemetry. In simple terms, the jet flew the way the math had predicted, which is exactly what the engineers needed to see before bolting a much more powerful engine into the next airframe. Mach 1's job was narrow on purpose. Its main mission was to prove that a drone shaped for high Mach work could still take off and land on a normal runway using conventional gear, which is a key requirement if future hypersonic aircraft are going to operate from regular bases instead of special launch sites. Once that box was checked, Hermeus could move to a larger, faster machine. That next step is Quarterhorse Mk 2.1, which is already flying. Mk 2.1 is roughly the size of an F-16 fighter, but it has no pilot inside. It is remotely flown and powered by the Pratt & Whitney F-100 core that will later be joined to Chimera's full combined cycle system. The aircraft has a sleek high-sweep wing and a pointed nose shaped to handle high-speed airflow. In early March of 2026, Mach 2.1 took off from Spaceport America in New Mexico for its first flight, using the wide-open airspace over White Sands Missile Range as its test playground. Hermeus describes this vehicle as the first in a series of Mk2 aircraft that will start subsonic, then break the sound barrier, and then stretch further into the high Mach range as the campaign goes on. Mach 2.1 itself is designed to go beyond Mach 2 once the test team is ready, making it one of the fastest unmanned aircraft ever flown. Right behind it on the drawing board is Mach 2.2, which the company openly calls a future world's fastest unmanned aircraft, and Mach 2.3, which will push these ideas even further. The goal for this whole Mach 2 family is not just a speed record for its own sake, but to give engineers the data they need on how the airframe and F-100 engine behave as they push through transonic and supersonic regimes again and again. All of that is still the warm-up act for the real monster in the lineup, Quarterhorse Mk3. Mk3 is planned as the first aircraft that will carry the full Chimera 2 engine and actually perform a live switch from turbine mode to ramjet mode in the sky. It will take off like the earlier jets, accelerate under F-100 power, then, at high speed, shut down the turbine flow path, open the ramjet path, and keep accelerating on that simpler straight-through burner. If Mach 3 can do that reliably, It will show that a reusable aircraft can cross the line from very fast jet into true high Mach territory without relying on rockets or throwaway stages. At the speeds Hermeus is chasing, no human can sit and hand-fly the jet in the old way. A half-second delay between a pilot's thought and a control input could move the aircraft miles off course. That is why Quarterhorse is uncrewed and why its brains matter as much as its muscles. The onboard systems have to sense tiny changes, adjust surfaces, and trim the engine in fractions of a second, so the vehicle stays stable while slicing through air that wants to flip it, cook it, or both. How Mach 5 jets could change the world. This whole story only matters if that new speed actually does something in the real world. A jet that can outrun its own problems is cool on paper, but the real question is simple. What happens the day it rolls out to a runway, lights the engine, and someone says, "Go"? First up is the warplane that does not carry a pilot at all. Hermeus is building something called Dark Horse, a reusable hypersonic drone built only for defense work. On the company's own material, and in outside studies, Dark Horse is described as a multi-mission, uncrewed aircraft, roughly 45 feet long, designed to reach around Mach 5 using the same hybrid engine family that powers the test jets. It is meant to fly high, fast, and come home to fly again, not burn up like a one-shot missile. Picture how that changes a normal mission. Instead of a slow spy plane taking hours to creep toward a dangerous coastline, Dark Horse rolls from an ordinary runway, climbs above airline traffic, and sprints in. At several thousand miles per hour, it can cross a region the size of the South China Sea in well under an hour, take a look, cause trouble, and be turning back out before enemy fighters even get close. Speed alone is not the trick. The real power is in how many jobs you can pack into one fast pass. A Dark Horse flight could map radar sites along a coast, watch which ones turn on, and send that live map back to slower bombers that are still hundreds of miles away. On the next run, it might carry jamming gear to blind those same radars for a few minutes, or drop small decoys that look like much bigger aircraft on enemy screens. This lines up with what American planners say they need in tight, heavily watched areas. In public writing about hypersonic systems, US officials talk about the push for tools that can slip into denied airspace in places like the Western Pacific, without parking big, vulnerable bases on a rival's doorstep. Hypersonic aircraft that launch from normal runways, hit Mach 5, and then recover on a friendly airfield fit that wishlist almost perfectly. But this speed race is not only about war. Hermeus has a second machine in mind that is meant to carry people, not sensors and decoys. That aircraft is called Halcyon. Company leaders and outside studies describe Halcyon as a roughly 20-seat hypersonic passenger jet, designed for around Mach 5, with a range of about 4,600 miles and a focus on more than 125 long routes over water. The target is trips like New York to Paris in about 90 minutes, with tickets in the same range as today's business class seats. A Halcyon flight would feel very different from a normal long-haul trip. The aircraft is planned to climb far higher than today's jets, up toward 90,000 feet, where the sky outside the window goes a deep dark blue and the curve of the Earth starts to show. Getting regular people through that kind of flight without hurting them is its own challenge. You cannot just slam a cabin full of passengers from zero to hypersonic in a few minutes, the way you can push a drone. The climb, the turn onto course, and the push to full speed all have to be smooth enough that people can stand up, sit down, and not black out. Black. On top of that, the cabin has to stay pressurized and safe at heights, where the outside air is thin and freezing, and escape plans have to work even when the plane is far out over the ocean at extreme speed. Hermeus has talked about leaning on lessons from its unmanned aircraft and on work with NASA as it shapes those systems. Noise rules may be the biggest break on hypersonic travel, and that problem is not in Hermeus's hands alone. Since 1973, the United States has banned routine supersonic passenger flights over land largely because of shock waves that hit the ground as loud sonic booms. To fix that, NASA and Lockheed Martin built the long-nose X-59 test jet to turn that sharp boom into something closer to a soft thump. Its first flight in late 2025 marked the start of a series of tests that will ask real towns what that sound feels like. If regulators are convinced, they could relax some overland bans in the future. Any hypersonic airliner, including Halcyon, would benefit from that change because it would no longer be locked to only ocean routes. Hermeus is not the only player trying to bend the speed curve. In the defence world, Stratolaunch is already flying a reusable hypersonic test craft called Talon A. In Pentagon-backed trials in late 2024 and March 2025, the Talon A2 vehicle was dropped from the giant rock carrier aircraft, lit its rocket engine, went beyond Mach 5 over the Pacific, and then came back to land at Vandenberg Space Force Base. The same vehicle flew twice in a few months, which made it the first reusable hypersonic testbed the United States has had since the X-15 program decades ago. On the civil side, Boom Supersonic is pushing a different angle with its Overture airliner. Overture is not hypersonic, but it is planned to cruise at about Mach 1.7, carry around 60 to 80 passengers, and fly more than 600 long routes around the world. The company says it will run on 100% sustainable aviation fuel and target fares similar to business class. A small prototype called XB-1 has already broken the sound barrier during test flights, helping prove that parts of the design can actually work in the real world. Europe tried its own big leap with a company called Reaction Engines. For more than 30 years, it worked on a special engine called Sabre that mixed jet and rocket ideas and used an advanced pre-cooler to deal with very hot air at extreme speed. The goal was a space plane that could take off from a runway, go hypersonic, and reach orbit without dropping stages. But in late 2024, Reaction Engines ran out of money and went into bankruptcy before that dream left the ground. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.